You're now hearing a sine wave. Let's examine a sinusoidal longitudinal wave. First we look at y equals a sine kx dashed equals a sine 2 pi x dashed over lambda. Again, a is the amplitude, k is the wave number, and lambda the wavelength. As before, x dashed is displacement in the frame that is moving with the wave. Y is the average displacement of the air molecules, but in this longitudinal wave, that displacement is in the x dashed direction. Look what the sinusoidal displacement does to the distribution of particles. There are alternating patches of higher and lower density. It requires pressure to compress air to produce a higher density. So, higher and lower density correspond to higher and lower pressure, depicted here by colour. A microphone measures the variation in the pressure from atmospheric. This variation in pressure is called the acoustic or sound pressure, and its symbol is lowercase p. Density variations in a sound wave are much harder to measure, and displacement is virtually impossible to measure. Note, however, that maxima and minima in pressure both occur in regions where the displacement is zero. So the pressure and the displacement are 90 degrees out of phase. Repeating our analysis for the travelling wave, x dashed is the coordinate moving with the wave. Let's use v for the speed of sound, so in terms of the displacement x in the stationary frame, x dashed equals x minus vt. And again, we write the travelling wave as y equals a sine kx minus omega t. Because of the 90-degree phase difference, we write the equation for acoustic pressure P using a cos function, where P sub m is the amplitude of the pressure wave. Differentiating displacement gives the velocity of the collective motion of the air. We see that, at least for this one-dimensional wave, the pressure and the velocity are in phase.